All right. Well, welcome to lecture 6, CS 2810, Mathematics of Data Models. Um, I am Professor Wu, and yeah, this is Northeastern University. Okay, so previously a vector. We talked about vector, and I wanted you to just think of it as a bunch of numbers enclosed by brackets. Okay? And then depending on the meaning we give to the vector or the matrix, then we can like use various manipulations to um, manipulate them. So one way to interpret a vector is to view them as an arrow with some kind of direction and length, magnitude. So if we look at a vector 2 and 8, you can see this is 2, this is 8. It's just an arrow with a direction. So that's one way to, and a very common way, in fact, to interpret vectors. Another interpretation is a point in space. So you see 2 and 8, instead of an arrow, it's just a point. If we interpret a vector as an arrow, what do you think is happening when you multiply a vector by a matrix? Okay? So you have this vector, which is what we had, 2 and 8. Now, if we multiply by a matrix, it gives us another vector, 18, 16, which is 18, 16. Okay? So essentially, when you multiply a vector to a matrix, it transforms that vector. In this case, it went from this arrow to this arrow. Okay. Now, if we were to interpret it as just a point in space, it basically moved from this point to this point. In both cases, matrix A, you want to think of it as it's a function, right? It's acting as a function that takes X as input and output Y. Okay? So a new way to think of this is we are putting this as the input and we're putting it into some kind of function. So matrix. So matrix A is some kind of function and it's giving us an output. So that's the new way we're going to start interpreting vectors and matrix. Okay, that this is some kind of input. You put it into a function A, and it gives you some kind of output. So today's today's lecture is all about all the different ways we can transform a vector. So if this is the input, what are all the ways we can make them like transform them? Among them, the easiest way, the easiest transformation is if you multiply by a zero matrix. If everything inside a matrix is zero, then your output is going to be zero. Okay. The symbol for zero matrix is just bold letter, and therefore, if you take x multiplied by zero matrix, it will just give you zero. Now, basically, if you have a vector, you make it so it's just a dot. Basically, the vector length is zero. Or you start from a point, 1, 1, 1, 1. What's happening is you're moving it to the center, which is 0, 0, 0. So those are ways of interpreting what's happening when you multiply by 0. So this is a zero matrix. Now, this zero matrix is analogous. So right now we're looking at essentially matrix versus numbers. So with numbers, you can kind of picture 1 times 0 is equal to 0. Here, if we have A, 0 times some kind of vector x, and it gives you 0. So what I want you to start seeing the pattern is that we want to start thinking of matrix and vectors more and more like in terms of numbers, in terms of how they act, that they're going to act very similarly. in many ways. So one example I just showed you is that there is an analogous version of 0 in matrix as well. There's also an analogous version for 1, right? So let's say you have 5 times 1, it's just going to give you 5 back, right? Anything times 5. So if you have a vector x and you want to multiply by something that gives you x back, this matrix will be the analogous version of a 1, okay? So the way you do that with matrix is through a matrix where the diagonal is just 1, only 1, and the off diagonal is only 0. Okay, let me show you another example. Let's say we have 3 dimension. 1, 1, 1, 0, 0, 0, 0, 0. Notice that the diagonal are all ones and the off diagonal are all zeros. Now let's do 1, 2, 3. If you were to multiply them out, you will see that output is 1, 2, 3. It's almost as if this x is multiplied by some 1 and it just gives you x back, right? So this matrix has a special name. It is called the identity matrix. The identity matrix it gives the identity back. Whatever you put it in, it gives it back. And the special symbol for identity matrix is just a bold I, okay? Or a capital I. Now, here's another one. Multiplying by constant. 5 times 2 is equal to 10, right? So now, if we have a vector and we want to make this vector multiple times, like 3 times, yeah, I think this is 3 times longer. How do we multiply by 3? Well, the way we can do it is if we have the vector, we can just multiply by 3. That's reasonable. Or in terms of matrix format, we can multiply by 3, 3. Okay? So this is how you actually extend it. Now, you can also extend just part of it. So let's say we want to double the first number while keeping the second number the same. The way you will do it is 2, 1. Okay? Now, you essentially double the first number, which is 2, right? And then the second number stays the same. So you can scale just one element, or you can scale multiple of them depending on how you pick the diagonal. Okay. If it's just one number that you're scaling, like everything is a 3, most of the time we write it this way. But I want you to notice that you don't have to scale every number in the vector simultaneously by the same number. You can scale it just by like one element or 2 elements, depending on how you pick the diagonal. Okay, rotation. So rotation is a special matrix where, let's say we have this vector, you can see is 1, 1, 1, 1, right? And we want to rotate it by 45 degrees. 45 degrees. So if you remember from your geometry, this would be 90 degrees and half of it will be 45 degrees. So the way you do it is you plug whatever degree you wanna rotate, okay? And this creates the matrix you want. So you plug 45 degrees in. Notice after you multiply this out, you're going to get square root of 2 and 1, right? Square root of 2, right? Square root of 2 and 1. So it previously was here, and now it has rotated. Previously was here, and now it has rotated onto this by 45 degrees. Okay, so that's how you do rotation. The way we can represent rotation is through a capital R with a theta here. So the example we just showed you, we want to rotate by pi over 4. So 45 degrees is equal to pi over 4. 90 degrees is pi over 2. So from this, you can essentially say, okay, I want to rotate my x by pi over 4. Or if you want to rotate the other way, you want to rotate this way, you want to rotate by minus pi over 4. Okay? Right. The next thing we can do, this is actually quite useful. It's called a permutation matrix. So if you have a vector and you want to rearrange the order, like keep all the numbers, but you want to rearrange them, you can use this thing called a permutation matrix. So, for example, notice if you multiply by this, then this and this, notice you're going to get 2. And then this and this, notice you're going to get 3. So by intelligently pick where the 1 value is, you can rearrange the order. You can even rearrange the order and increase the scalar. So for example, let's say you want, after rearrangement, this 2 times 2. Okay? So if you put a 2 here, notice instead of a 1, like, you're going to get a 2. So you can simultaneously scale and rearrange the numbers. And this is called a permutation matrix. You basically just put a 1 at the location. So you want the second one to be in the first location, right? So notice when you multiply it down, you got 2. Or if you want the third one to be in the second location, so this is the second location, and 1, 2, 3, the third one. So the way you would pick them intelligently is basically pick these ones at the spot which will allow you to do rotation. Now, permutation matrix is quite useful in a lot of settings. For one, we can use it to model like activities that go from one state to another. Let's take this one, for example. Let's say my schedule is I start from home, I go eat some brunch, I go to work, I go to gym, then I go home again. So this is like the cycle every single day. And I can represent these 4 states with a vector. So if I'm home, I can say that's the first one, right? So this is equal to home. When I see this vector, that means I'm home. Now, if I see this vector, it means I'm at brunch. So notice the first state is home, the second state is brunch, third state, and the fourth state is gym. Okay, so we can actually mathematically model my day using this. And if you intelligently pick the permutation matrix, it will look like this. Let me show you how it works. We start from home, right? We start from home. So when I'm at home, if I plug 1000 into the permutation matrix, what it will do is it will tell me what the next state is. So now, if we multiply this out, notice that you will get a 1 here. So it's telling me that I start from home and it's going to end up at work. Sorry, end up at brunch. So notice this is brunch. So the input is home, the output is brunch. So this allows me to essentially mathematically model what's happening here. That I start from home, and that next one is going to give me brunch. And the next one, if I plug brunch into the same matrix again, is going to give me work. So let's take a look. So now that I'm at brunch, if I plug brunch into the function, remember we're going to treat this as a function. So we plug this into the function. Notice the output is the third one, work. So I went from home to brunch to work. And if I keep going, you will see that I will reach gym and then home again. And then the cycle will just continue. So you can see many aspects of life, you can model like the states. First, it's going to start from A, and then it's going to go to B, and then it's going to go to C. And by modeling that way, you can describe the entire process with this thing called the transition matrix. Okay. Now, um, um, for a long time, so for a long time, when I was younger, I think when I was in college, I remember trying to solve Rubik's cube, and what I did was I represent a specific orientation of a Rubik's cube, like as one of these, right? And then I had each one of them would mean a different orientation. And then I would manipulate the the Rubik's cube in some way, and then I will see that it will move from this day to this day, or this day to this day, and I was able to collect whole bunch of permutation matrix. So what I did, I had like P1, P2, uh, and then P3. So each one of them is a different way of how things are going to uh, move from one state to another, depending on the move I make. And if I were to if I were to do input the current state, right, multiplied by p, and then p1, p2, p3, then I can essentially say, oh, this px final is the state I want. So what I could do at that point is I could mix and match different like permutations so that the final state is given to me. And I wrote a program to do this so that it would essentially tell me exactly how I would turn the Rubik's cubes to solve it. So it did work, but that was like an example of real life of how I used it in the past. Now, here's another transition state. This one is pretty easy. Basically, we have a singer. Not sure if you ever heard of her before, but anyways, imagine if this is her day, right? She starts at home. She goes and visit her favorite computer science professor daily, which is me, and then she goes to plays in a concert, and then she goes and start iteratively print money. So she just print money over and again. So I want you to pause the video and see if you can solve this. Like create the transition matrix. Okay, I hope you pause the video because we're gonna try to do it together. So let's say we have home, which is 1000. So that's home, and then visit is 10100, and then play is 0010, and money, printing money, is equal to 0001. Okay. Now, if we form the permutation matrix, we want, if we plug 1 in, right, we want that to equal to 0100. So that would be, let me see. So it's saying that the second one has to be 000. Okay. So the first one we don't know yet. Third and fourth we don't know yet. Okay. Now, if we're in the second state, 101, we want that to be in the third state. So we want to move it to a third state, which is playing concert. So let's see. We want that to be in the third. Therefore, it goes like this: 0100. Right? So if we multiply the first one, yes. So only when we are multiplying by the third row are we going to end up like with a 1. Okay, so let's continue. So next, if we're at the third state, 0, 0, 1, 0, we want it to be in the fourth state, so 0, 0, 0, 1. So that means the very last row, 0, 0, 1, 0, that will give us this value. And now, if we're in the fourth state, let's see. So it'll be 0, 1, right? So the fourth state. And we want that to remain in the fourth state. 1, 2, 3, 4. So how could that be done? I think you have to put a 1 here. You have to put a 1 here. And then all these are zeros. I think that makes sense. So yeah, I think that's how you have to do it. Let's see if it's true. Let's pick the first one. Okay, first one's 1, 0, 0, 0. What do we get? 0, 1, 0, 0. So that's right. It moves to the next state. Now let's try 0, 1, 0, 0, and what happens? That means we have 0, 0, 1, 0. So that moves to the third state. So that's fine. Now if we have third state, 0, 0, 1, 0, where does that go? That goes to the fourth state, 0, 0, 0, 1. And if you're at the fourth state, 1, 2, 3, 4, then it would be, it stays at the fourth state. Yeah, it's because when you're at the fourth state, you don't go home. You just keep going. So this is the permutation matrix. And that's how you can describe like somebody's day. Okay. Next, if we have multiple points simultaneously. Now, we were doing transformation of just one point. What if you have 2, 10, 100, 1 million? Can you efficiently do all those points, transform them simultaneously? And yes, the way you would do it is that you would stack them. You would stack the points this way, vertically. So the first point was 1, 1. Here we go, 1, 1. And then the second point is 1, 0, which is right here, 1, 0. So if you stack them, instead of a vector, it is now a matrix. So let's say we want to rotate every single vector here by 45 degrees. So I would take the matrix, multiply it, and then this is the output. Now notice it simultaneously rotated both points so that this goes here and this goes here. So notice the first one went and the second one went. So this is, you see the 45-degree rotation. All right. So that's how you do multiple points simultaneously. You just stack them up this way. And that's much easier than doing one at a time. Here's another example. Let's say we have a matrix, right, that represent the running record for 1,000 people. So it's 1,000 people this way, and there's 7 days of the week. So these are the number of miles they ran. So therefore, each person right now is a vector, right, and it's stacked this way. So if y represent the total mile ran, like this week per person, and ax is equal to y, then what is a? So let's say you have each person, and you want to convert it so that you get the sum. So the first person maybe ran 5 miles total, and the second person maybe ran 7, and the third maybe ran 10, and so on and so forth. So you want to go from this matrix to this vector. Okay? So the manipulation right now is summation. The way you can do this is by multiplying x by a matrix that looks like this. So if you just put all ones, it's essentially summation. Let's say we have 1, 2, 3, 1, 0, 1. Okay, so we have two people. And if you do this 1, 2, 3, notice when you do this and this, it's going to sum them up. So the result would be 6. And then you repeat this and this, you're going to sum them up, and the result is 2. Okay, so this right here is a summation. And with the summation, of course, it's also subtraction, right? You can put a negative, or you can do averaging, like 1 over n. So 1 over 3 here, that will give you the average. Later on, I'll show you centering as well. So from this idea, a lot of things could happen. The way we like to represent this vector of ones is with a 1, like this. So if you see 1, this is a vector of ones. And maybe you'll see 1, 7, or 1, 7 this way. So this kind of tells you the dimension. If you see just 7 here, it's a vertical vector of ones. 1, 2, 3, 4, 5, 6, 7. 7 tells you how many ones are inside it. Okay. So that is the one matrix, one vector. Oh, also, if you have this format, so this is 1 by 7, right? So 1 by 7. 1, 2, 3, 4, 5, 6, 7. You can also have one that says 2 by 2. 2, 2. And this would tell you 1, 1, 1, 1. Or 2 by 3 would be 1, 1, 1, 1. So 2 by 3, 1. So it basically can be either a vector or a matrix. All right, I think right now it's time to practice identifying the transformation. So let's say you have x and you want to transform x into these, right? Or you want to take x and you want to transform into these and these. See if you can find the appropriate transformation for this. Wait a second. Let me think. Oh, no, it's this. So you want this to transform into these. Oops, where it jumped. Here we go. Okay. So it might be confusing how you might get this. I think it's easier with these 3, but these 2, you want to think about it. And the second one is you want to use this and see if you can transform into these. Okay. All right, well, I think that is the end of part A of the lecture. So I'll record another one for part B. This lecture is particularly long, so yeah, you want to take it one step at a time. All right, thank you. See you later.